So good morning, everyone. Welcome to the third lecture of Professor Janelidze on mathematical proofs with Python. Zurab, I don't need to introduce you anymore. People have met you already at least twice. So you're most than welcome to share your screen or your various gadgets and start with your presentation. Thank you very much.
Thank you very much. It's very exciting, especially to interact with the audience here, of course, but also afterwards on Moodle through completion of various activities. I am planning to make a recording of a kind of feedback on the various homework that has been submitted through Moodle, a separate recording, then I will provide a link for. I will do it over the weekend. But for now, let's continue with the material. My impression was that those who participated in the submissions, most of them got things right. So I think we can continue. But if there are any burning questions before we continue, I'm also happy to first spend a few minutes on that. So if you have any burning questions that you feel we need to address before we continue, please do ask them. So if not, then I'm going to continue. So we're going to today's lecture is I think more interesting than the previous two. We were kind of building up some background in the previous two lectures, and today we're going to see a bit more of the actual proofs. But there is still one concept that we need to cover before we are able to tackle some interesting proofs, and that is the concept of a constant. And I'm going to explain that concept on the blackboard. So there is a difference between, okay, so let me first, sorry, do this. If I write something like this, x plus y equals 2. There is a difference, of course, between x and 2. In this case, x is a variable, as we can see from the definition of a variable, and 2 isn't. When something like this is stated, right, then 2 together with the equality sign and with the plus sign becomes one gadget, right? If I consider ontology of this statement, in the step below, I will simply have the statements x and y. So we see that 2 is completely lost here. That means that Sophia will not be able to recognize 2 as a separate object, as a separate number. And we don't want that. We sometimes want to work with numbers as well, as separate objects, not just variables, right? So maybe one way of solving this problem would have been to include 2 as well in square brackets. Then the ontology would then also include 2 as a separate object, and that seems to solve the problem, but not quite. We don't really want to do that. And I would like to ask audience to point out why we would not want to do that. So what would be wrong with putting 2 in brackets like this so that Sophia now can recognize number 2 as a separate entity, just like x and y? Feel free to either raise your hand for answering the question through microphone or type it up in the chat. So the question is, what would be wrong with having the fact that x plus y equals 2, stated the way it is shown on the screen, with 2 appearing in square brackets as a statement, just like x and y. Exactly. Very good. Thank you so much. So we have 2 answers in the chat, and both of them are correct answers from slightly different angles. So if we do the way I wrote now on the screen, what would happen? The effect of this would be that Sophia would treat 2 as a variable, just like y and x. So if I continue with the ontology, we get this, and then we see that 2 is now treated as a variable. And we don't want 2 to be treated as a variable, because a variable can change value, and 2 is not supposed to change value. 2 is supposed to be constant. So this is the idea of constants. When we want an object that is not a variable, the question is how to represent it. There is an easy solution to this, and the solution is the following. We enclose 2 in brackets, but we attached 1 pair of brackets with no contents in it. Now, when we do that, the role of 2 becomes somewhat similar to the role of, let's say, plus here, where if I look at the ontology, so first of all, this statement should turn into a formula, right? And then the next step is for this to turn into a statement. And we can't go further, because if we try to go further, we will get an empty character, right? But I mean, we could write the empty character if we wanted to. So this lower part, you see, it is always going to look like that. So then we can agree that if I have a formula whose lower part always looks this way, exactly this way, then that formula actually is understood as a separate entity by Sophia, but no longer as a variable, because in the case of a variable, we have nothing below, you see? Okay, so that explains what a constant is, and the purpose of also of a constant has been explained this way. Let us now look at an example of a proof which makes use of this idea. I'm going to copy paste this code. We're going to complete the activity shown here. And let me open the spider, paste the code there. However, let us try to do this line by line. Okay, so just a reminder that with the first line, of course, we're importing the Sophia module. And then with the second line, we are creating a proposition. This S is a proposition. This proposition is called Sophia can prove. So we will eventually turn it into a theorem, which will be stating that Sophia is able to prove, more or less. Now I open up the first line of the proof, and what we see in the first line of the proof, let me compile this. So here we have our theorem, Sophia can prove. There is no theorem yet, because just with that first line we have proved nothing. We only have one line in the proof, and this single line is indicated at the end of the line is an assumption. And the assumption is what is stated here. So let me remind you that this colon represents implication. So we're basically saying here the following. So if I now look at this whole statement and try to consider its ontology, so it consists of this part stating Sophia is human, and you see that Sophia appears with these spare brackets like this, so that it is interpreted as a constant. So it's not a variable anymore. It is some fixed entity. And of course, in our minds, it is the program Sophia herself. So we're saying here that thing, that Sophia is human. Well, probably it's not true, but let's assume it is like that. And then the next statement we're making is that this whole thing. Sorry, just one moment. I got lost myself here with brackets. Yeah. The next statement is this whole thing. And let's see what it's stating. I think I might need Roy's help. Okay, sorry. Yeah, no. I don't need Roy's help anymore. By the way, Roy Ferguson is helping me with this module. He's been answering lots of questions from the participants. Thank you to Roy for that. So this statement consists of two statements, right? This one and that one. The first one is stating that Sophia is human, and the second one is stating that something implies something else. So here we have implication sign, the column. On the left side of implication, we have X, and X is human. And then on the right side of the implication, we have X can prove. So this whole thing is saying that whenever there is some X that's human, so whichever human we pick, we find that human will be able to prove something. It has the ability of proving things. Okay. So this is a general statement that concerns all human beings. And its generality is given by the fact that we are using a variable here. So this is true for every X. Why? Because we said it must be true for X, but X is a variable. And the point of a variable is that it can obtain various different values, right? On the other hand, the left side of the statement says that Sophia is human. Now, before I open up the next lines of the proof, would any one of you like to explain how can we deduce from the fact that Sophia is human? So that's one fact we have separately, and the separate fact that every human being is able to prove. How can we deduce from these two separate facts that Sophia can prove? I invite you to unmute your microphone and to perhaps try to explain that. So while you're thinking about it, maybe I'm going to give a visual image that describes this statement. Let's draw the ontology of this statement. So we have Sophia is human. And next to it, we have another statement saying that given X, that's human, given that, as an assumption, we can conclude that X can prove. Remember that this symbol here represents mathematical implication. So in mathematics, we usually write it this way. The ontology of this would be, so we basically have two statements, right? So then it decomposes into formulas. The first formula would be this. And the second formula would be this. And by stating those two formulas using synopsis as given in the first line, we are claiming that both of these must be true. At least that's our assumption, that both of these are true. because remember, it appears in the assumption line. So the line 1 is an assumption in our proof. So it's easy to interpret this. It just says that it's claiming that Sophia is human, and the interpretation of this, just to replace the colon with the usual implication symbol, it says that every human can prove, right? Here, on the other hand, we have that Sophia is a human. Sophia is human. And now the question is that I asked, from these two facts, how can we conclude that Sophia can prove? Would we be able to logically conclude from these two that Sophia can prove? So please unmute your microphone, explain that if you would like to. Thank you very much. Indeed, so one answer came in. It says, if Sophia is a human and a human can do proofs, we can then say Sophia is human, thus she can prove. Of course. I think it's a very obvious logical idea to be able to come to this conclusion from the other two statements. The statement on the right-hand side here is a general statement. It concerns all human beings. And on the left-hand side, we are saying that Sophia is one specific human being. So if some property holds for everything in a group, and we pick something in that group, so we pick Sophia from the group of all human beings, of course, Sophia will also have the same property because we know that it holds for everything in the group. Now, the logical rule that we use here to make this conclusion, we think of it as specialization because we have the general property that we're specializing to a specific human being, a specific member of the group, is one of the, in a way, in some sense, it's one of the most important rules of logic. We call it a deduction rule because it's one of the rules which we can use to make deductions or conclusions in a proof. And so now let's look at this. How this is done on our code, in our code. But something interesting is going on. We have a second assumption. Instead of saying what we just said, that we can now conclude that Sophia can prove, instead of that, we have a second assumption. It didn't like something. Sorry about that. Let's see what's happening here. Oh, there is an error. Or am I pressing? Sorry, I think I was pressing the wrong button. I was pressing debug instead of run. There we go. Okay, so you see what happens here in the proof. Instead of simply concluding what we agreed that we would conclude, that Sophia can prove, we are now introducing another assumption, which simply states Sophia. What do you think is the interpretation of this? Why are we doing that? What goes wrong without having this line? Would anyone like to take a guess? Why do we need to assume simply Sophia without any other properties attached to her? What is the significance of this? Absolutely. Thank you very much. So an answer came through in chat. It says Sophia has to exist first. Exactly. Without knowing that Sophia actually exists, we would not be able to do anything. Why wouldn't we be able to do anything? Because if we look at this implication here, it says that every human can prove, but not just that, every human that actually exists, a human needs to be given first, an object needs to be given to us first. It's not enough that we know that this object is human, we also need to know that the object exists. Only then we can conclude that that object can prove. By object, I'm referring to X now. We do have this information that Sophia is human, so this matches with that part, but we didn't have so far anything matching with this part, which was assuming that Sophia would exist. And also, if you remember from the discussion, the previous lecture about scope of variable, we absolutely needed this here, because if that wasn't here, then this X and that X wouldn't be able to recognize each other. So you can think of this as a general mathematical principle saying that if you want to make statements about things, the things that you're making statements about, first, they have to be assumed to exist. You can't talk about things which do not exist. Now, in mathematics, of course, we talk all the time about things that don't exist necessarily, right? But it's okay if they for real don't exist, but at least we have to assume they exist. That's the general philosophical idea behind this. Okay, so now that we have assumed that Sophia exists, and we also have that Sophia is human, so these two statements we have, right? We can now take this statement and specialize it to making X equal Sophia. And that is what's happening in the next line of the proof. So this D stands for deduction, so making a deduction, because it's one of the, as I said, it's actually the most important deduction rule. So we reserve the D for that. And now let me explain what these parameters do. Parameter number 1 tells me where is the line where my implication to be applied resides. This is the implication I want to apply, right? I want to apply this fact, sorry, it's this one. I want to apply this fact to X being Sophia. So this is my implication I'm applying, okay? It resides in line 1. We see that it resides in line 1. So we put number 1 here. So that's the line number of wherever our implication resides. Now let's look at the next parameter. This thing here will be a list of coordinates. I could have another item in this list, like 3, 4, for example. It tells us where can I find those objects to which this thing needs to be applied. So in other words, what should X be when I apply the implication? To what value should X concretize? In our case, we want X to be applied in the case of X being Sophia, right? So I'm going to tell the program, look, I want this X to be specialized to this thing that I know exists because it appears as a separate statement. And so then I have to give the coordinates of this thing. The coordinates are determined by line number and position of your atomic statement in a longer statement. So line number here is 2, right? We see that line number is 2. And position is 1 because there's nothing else here. If there were other statements next to it, the position would still be 1. But if there was something on the left side of it, then the position would increment by 1 as many things on the left side we attach. As many statements on the left side we attach. I only want to apply, I only have one free variable here, X, to use. So I'm not going to list the second coordinate. I don't need it. So I delete that. I just inserted that for explanation that there could be several of them. And then the last parameter tells me the position of this implication, because it could have been that the first line only contains this implication, nothing else. Then I don't need to enter the position. Then I could have just entered like this. But because the first line contains another statement, I need to tell Sophia which of these two I'm going to be using for my next step. and it's the second one. So the position of this thing is 2. When we will run this, what do we expect Sophia to produce in the next line? I would like to invite you to type it up in the chat. But before that, I see that there is a question from Eric.
Thank you very much. Would you mind repeating what you explained just now? I got a little bit confused, but as you repeat, maybe I can just qualify my statement, my question. The line that you explained right now, you put in coordinates and line numbers, and those line numbers and coordinates are actually coming from the output. So do you run the code first so that you get the coordinates, then you go back to the input and then update the input?
Yes, exactly. Remember, when you're designing a proof, you're designing it line by line. So the previous line we had this, and when we ran it, it showed us this. So I do need to run, I mean, unless I can imagine what's going to happen, I do need to run it every time before I add the next line.
Okay, yeah, but yeah, so maybe if you can just go again, yeah, on that one, yeah, I think that then that it'll help me a lot.
So should I explain again the meaning of these parameters?
Yes, thanks.
I will do it with great pleasure. Maybe in that case, it will be nice if we can, instead of just explaining it verbally, it will be more clear if I draw at the same time. So the first line of the proof has, so what I want to draw now is just to draw the coordinates. So it becomes clear what the coordinates are in each case, and then I can explain through that. So we have that as a separate statement, and then there is another statement next to it, which says this. So this is one statement, and that's another statement. How do I know that this is one statement? Because the brackets match, right? So all the opening brackets have been closed, and that's how I recognize this to be a separate statement. The same on the other side. Both of these statements reside on line 1 in the proof. The position of the first statement is 1. The position of the second one is 2. Now let's look at the second line. The second line just has this, right? This thing is a statement of its own. And the line number for this statement is 2. It's the second line. Position is 1 because there is only one statement in this second line. There is only one atomic statement. By atomic statement, I mean the one that cannot be decomposed further into smaller statements. Like, for example, this statement here wasn't atomic because we were able to decompose it into 2 statements, this one and the other one. But this statement is atomic because we can't decompose it further. Okay, well, now we know in physics that we can decompose atoms further, but there was, I guess, time when we couldn't. Okay, so now how does this relate to the command s.d 1,21,2. So let's explain that again. The number 1 here refers to this number 1. It tells us the implication I'm going to apply, in which line does it reside? It resides in line 1 because we're applying this implication here. The second parameter is a list of coordinates. So this list only has one coordinate. You know, in Python, lists are given by square brackets, right? So it's a list of coordinates and it only has one coordinate. The coordinates being 2, 1, and these coordinates 2, 1 refer to this. You see line 2, position 1. What is the meaning of that? The meaning of that is that the unique variable we have here will get interpreted to have this value, whatever stands here. So that's the meaning of referring to coordinates 2, 1. This is remember, this is a general statement about arbitrary x, and we want to specialize it for specific x. And we're basically telling Sophia which specific x we must pick. And the answer is this. And finally, this parameter here corresponds to this value there. So it tells us the position of the implication. Now, the reason why this parameter appears at the end is that a lot of times, the line in which my implication is will only consist of that implication, nothing else. So that the user doesn't have to enter extra information. We can just drop that, and then we could just have that. So the last parameters in Python can always be dropped, but then they must have some default values defined in the function definition of that command. But in this case, that's not true. In this case, the first line contains 2 statements. So we do have to enter the last parameter, which is then the position of our implication. It's the second position. Okay, so does this, Eric, does this answer your question?
Yes, it does. Thank you so much.
Thank you. And then I asked what would be the expected outcome of this next line of the proof, but accidentally I also showed it, but maybe you didn't notice. So would you like to write out in the chat, what do you think would be the expected outcome of this fifth line in the, fourth line in the proof? Well, actually the third line in the proof. Fifth line in our code, but it will be the third line in the proof. The outcome itself will be in the third line. So if you think about it, we had a general statement that every human can prove, and now we're specializing this to Sophia. So we basically should get a Sophia version of what we said before, namely that Sophia can prove. So just typeset in Sophia syntax. So how do you think this would look like? Sophia can prove with this with the Sophia syntax. Okay, so I see that nobody's typing anything yet. We're not going to step out from assumption yet. We still want to, so someone said that we should be stepping out of the assumption. So there is an answer in the chat. It says, Sophia can prove, and let me actually discuss why that answer is incorrect, because I think it's going to be revealing to explain why it's not correct. So an answer came through, which looks like this. I guess this should be capital X. So what is wrong with this answer? Well, it's actually not far from being correct, but it's not quite correct. So first of all, we don't need X anymore. What's the use of X? We already specialized X. There is no need to talk about X anymore. Secondly, Sophia needs to be a separate entity. So we actually need to have brackets like this around Sophia. And then with it, we need another bracket there. And of course, it's just English adjustment here. We need prove, not prove. Prove is a verb and proof is a noun. So if I look at it from the perspective of the original statement, you will see that basically what happens is that you see this thing here matches with that, except that instead of X, we have Sophia, right? So basically what happens is that since this column is supposed to be implication, Sophia confirms that the left-hand side of the implication are things we already have. We already have X, but more specifically, we have a specific X, which is Sophia. And then we already have that X, which is Sophia, is human. And that we have here. So Sophia, the program will search for this value inside the proof as one of the statements in the proof, replacing X with Sophia as we instructed. And if she finds that both of these requirements are fulfilled, that we actually have Sophia, well, we told the program what it was, and then we also have that, then by the rule of implication, remember implication in mathematics means that whenever you have one thing, then you can conclude the other. So then she's able to conclude this for us. But now that X became specialized, right, she will conclude this for us with a specialized X, namely replacing X with Sophia. There is a question whether we are missing an opening bracket. Eric, if you're asking about what I wrote, I don't think there is a bracket missing.
Okay, I thought there will be a bracket which starts at can prove.
No, because if you look at originally here, there was no bracket like that there. So this part is X, yeah? If I replace that Sophia with X, I get exactly the same as I had before.
Oh, okay.
Okay, so now let's see if this is really, thank you. Let's now see if this is really the result. We run it, and indeed, it's exactly the output. On the other hand, however, look, if I look at the statement of my theorem, still I have proved nothing. Why is that? That's because, as Isaac told us a bit earlier, we need to step out of the assumption. So what does it mean to step out of the assumption? At this point in the third line, we have a bunch of assumptions. We have this assumption, we have that assumption. We're in the middle of a proof. We're in the middle of a discussion. I now want to summarize my discussion. I want to drop all the assumptions and tell the world universally, look, this is the true theorem that I've established. Because the world doesn't know about my assumptions, I cannot. It's a bit like this. When we have an assumption opened up, like there is this bracket that opened, right? And the assumption has been closed yet. It's a bit like having some thoughts that are in our mind that influences the way we think. Now, when I write down my thoughts on the paper, right, I need to bring out all my thoughts explicitly on the paper. So it's not sufficient just to have this, because this is only valid if that is true and that is true. And this has to be explicitly mentioned. I step out from an assumption by the synopsis rule, and this shouldn't be confused with the synopsis in the ontology. So what synopsis rule does, it summarizes what has been proved with the latest assumption. And if I run this, you will see the effect. So now the bracket that was opening up in this second line, this vertical bracket, has been closed. And right after that, we have this, which tells us the following. If I assume, remember this is implication, the column. It tells us if I assume that Sophia exists, then I am able to conclude that Sophia can prove. Right? Indeed, when we assumed in second line that Sophia did exist, that was an assumption, remember? It says here, it was an assumption. We were able to conclude that Sophia can prove. So then we can say that if I do assume, then I can conclude. So something that we did step by step now becomes a single statement stating in mathematical implication, that assuming this gives us that. There is still an assumption block we are in. It is the first assumption here, which is saying that Sophia is human and every human can prove, right? We assumed that, and using that assumption, we were able to conclude that when Sophia exists, Sophia can prove. So we haven't proved that if Sophia exists, Sophia can prove. We only proved that this is true under this assumption, not in general. If we didn't have this line 1, we wouldn't be able to carry out the proof. So when I step out from that assumption on line 1, I will get the following. This is what I will get. Now this long thing simply combines this statement with that statement, inserting colon in between. And here's that, where is that column? Here's that column, this one. In line 5, we no longer are inside any assumption block. So line 5 is universally true without any assumptions needed. And because of that, for the first time now in our proof, Sophia states this as the theorem we proved. So once all the assumptions have been dropped, once we are no longer having anything in our mind, whatever we've written on the paper has the full information, then we can publish that. Sophia recognizes this thing as the theorem that was proved. So whatever appears on the last line of your proof, provided that thing is not inside an assumption block, Sophia will recognize that as the theorem to be proved. And in general, in mathematics, that's how it works. So proof is a sequence of steps which leads you to the theorem you wanted to prove. So your last line should be the theorem you wanted to prove. In mathematics written out in language, we usually say, therefore, we have proved, and then we repeat the statement of the theorem. Okay, I think this was a bit, a few new concepts here, so perhaps there are some questions. I'm happy to take questions.
There is a question or... no, sorry.
Hello, Ilya.
Hi, Zurab.
Okay, so if
doesn't seem to be the case, yeah. Sorry.
If there are no questions, then let's move on, but we're not going to move on too far. We still want to understand this idea of introducing assumptions and then making conclusions. And we're going to do another example where it's going to be a difficult example. But it's also something that is very, very well known. So I don't know if you've heard of this paradox called Russell's paradox. There are many ways of formulating this. One of them is formulated using a barber. So one asks the question, is there a barber who shaves those and only those that do not shave themselves? And now if you assume that there is such barber, then you ask whether this barber shaves himself or not. And if he does shave himself, remember he was shaving only those who don't shave themselves. So if he shaves himself, then himself must be someone who doesn't shave himself. So he can't shave himself. But on the other hand, if he doesn't shave himself, the barber exactly shaves such people that don't shave themselves. So if he doesn't shave himself, then he must shave himself. So we get that this barber at the same time shaves himself, but at the same time not, and hence the paradox. And it is actually not a paradox. Paradoxes do not exist. Everything has a logical explanation. And in this case, the logical explanation is that we get this absurd situation that this barber at the same time shaves himself and not, simply because we assume that such barber exists. So the solution to the problem is that such barber does not exist, because it's assuming it exists, we get an absurdity. And as we discussed before also, how to prove something is false is to derive absurdity from it. So we're going to look at a version of the barber paradox, but I slightly reformulated it because you can read up on barber paradox everywhere on the internet, so it's a bit boring to do the same thing over and over. So I slightly changed the paradox, and it is the following. So let's discuss this first. I'm going to first state the statement that we are going to try to prove it. It's actually going to be a formula, but we will turn it into a statement. And then I'm going to explain what it says and explain how it relates with the barber paradox. And then we will try to prove it. Okay. So here is what we're saying. If we are given X, that is such that whenever we are given another X, so we are distinguishing these two X's with capital X and baby X, we have the following. So this is my barber, but it's not going to be a barber anymore. This is going to be now a teacher. And this is all the other people that the barber will shave or not. So in our case, this is going to be everybody else, all the human beings that the teacher will either teach or not. And so if I'm saying that if I'm given some human being or some creature, doesn't have to be a human being necessarily, then two things will be equal to each other. Two statements will be equal to each other. So I'm going to say that two statements are equal for arbitrary X. So I'm putting equality sign here. Maybe I'll need more space. So the fact that big X teaches small x, that fact, so let's write it. This teaches small x. So this is the specific person we're talking about. Once we assume that we have some x, it becomes some, it's a general variable, of course, but once it's assumed that it's there, then it becomes something specific under our assumption. So this capital X is someone who will, about whom, if we say that capital X teaches small x, that's exactly the same as to say that the fact that small x teaches herself, that fact implies some absurdity, namely that the world is flat. Okay, so let's try to understand what we're saying here. This part here tells me that if small x is able to learn things by herself, right? So x teaches x means that x is able to teach herself or teach himself. Then the world is flat. So we're basically saying that there's no way that X can teach himself. So we were saying that this person is not able to learn things by himself. Okay, so small x is someone who cannot learn things by himself according to this. X cannot learn things by himself. On the other hand, this statement says that X is a teacher of small x. Now, by making the equality between the two, we're basically saying that being a teacher of X is the same for X to be able to learn by himself. So this capital X is a very, very useful teacher. Why? Because it teaches exactly those people who are not able to learn by themselves. I mean, what's the point of teaching someone who can learn things by himself, right? So the capital X is in some sense ideal teacher. It teaches exactly those people, all of them, and exactly those who cannot learn things by themselves, right? And the fact that this is universally true for every X, for every small x, is marked by the fact that we have small x here and then colon. So every time I'm given some human being, so every time I'm given some human x, it follows that this x being taught by x, the small x being taught by capital X, is equivalent to the small x not being able to teach himself. Okay, now let's close the bracket here. If we are given that such ideal teacher exists, so X exists, which has this feature that it only teaches those students who are not able to learn by themselves. If we are given that, then from this we will be able to logically conclude that the world is flat. So in other words, we are saying that it's impossible. That's a paradox, that you cannot find such a teacher. And it's quite remarkable because intuitively, if you think about it, what's the problem? Why can't we find such a teacher? Let's simply do that. Let's become such a teacher. Let's only teach those people who can't teach themselves. And the problem is that we run into the problem with ourselves. So are we able to learn things by ourselves or not? And then it's similar discussion as with the Barber paradox, but now we will experience this in setting up the formal proof. Okay, any questions so far? So what we've done so far, we've stated the theorem that we will prove. So to turn this formula into a statement, I'm going to have another pair of brackets here. Does anyone have any questions about this? It's so long, it doesn't fit on one page. Maybe I make it a bit smaller. So
no questions.
So the idea is, if intuitively we all understand what we're trying to prove. Okay. Then let's start proving it. Great. So as always, the first line imports the Sophia module, and the second line creates a proposition named T. And the name of this proposition is Paradox of an Ideal Teacher. So it's a name we invented just now because, as I told you, the paradox exists in some other forms. This form of the paradox I created specifically for our lecture. Let's look at the next line. What the next line does, and we can run it to see what it does exactly. So it creates an assumption, and this assumption is exactly what we discussed. So it's an assumption that there exists X, which is such that no matter what object small x we consider, the fact that X teaches that small x is the same, so equality means is the same that the small x is not able to teach himself. And the way we express this is that if X does teach himself, then the world must be flat. So it's so absurd that X is able to teach himself that if we assume it does, then the world will turn out to be flat. We know the world is not flat, therefore it just means that X cannot teach himself. Okay. Any questions so far? Remember with the barber paradox, what we did immediately after assuming that there is a barber that shaves only those who don't shave themselves, we immediately considered the question whether this barber shaves himself or not. So what we want to do now is in the next step is to take this implication. It's an implication, right? We have a column here. It says something for every value of small x, and apply it in the case when small x obtains the value of capital X, so that we will be then considering the possibility of capital X teaching himself or not. Okay, and we already are familiar with this rule, the D rule, the deduction rule. And now let's explain the parameters once again. So this is the line number where our implication resides. Our implication resides in line 1, so it's just 1. The next is the list of concrete values of small x, and we will be substituting capital X inside small x. So and it resides on line 1 and position is 1. So coordinates of that is 1, 1. And finally, this number 2 refers to the position of the implication, and like before, position of this is 2. So on the first line, there are 2 statements. One is this, position of that would have been 1, and position of this implication is 2. And let's see what happens now when we apply that. Now we get, like before, so this has been concretized to capital X, and so Sophia will output whatever is on the right side of the implication, which is what she output here. And what this says now is that the fact that X teaches himself should be the same as the fact that X teaching himself implies the world is flat. So basically, this says that X teaches himself, right? And this says that X does not teach himself. So we now got in the second line equality of 2 facts: one that X teaches himself, and the other that X does not teach himself. In other words, if he does teach himself, we get absurdity like the world is flat. So we have equality of 2 statements which seem to be opposite to each other. One, X teaches himself, the other, X doesn't teach himself. What will follow after is a few steps of logic that will allow us to take this silly situation when something and its opposite are equal and eventually come to absurd conclusion from that. So the next few steps are very general. It could have been applied to any other situations where you have equality of something and its opposite. If you remember the way I explained the Barber paradox, I said, let's consider the question whether X teaches himself or not. And then I said, if X does teach himself, then because X teaches only those who don't teach themselves, X should not teach himself. So this fragment of my explanation, we now embody in this proof. We're going to assume that X teaches himself. You see, it's an assumption. But now look what we have. We have this assumption that X teaches himself, but in the previous line, we were told that this thing is the same, it's equal to that thing. So we could use right substitution, which we are already familiar with, and conclude the other part, right? So because I've assumed that X teaches himself, and because that is the same as that X teaching himself implying world is flat, we can conclude that X teaching himself implies world is flat. The difference between line 4 and line 2 is that in line 4, we're actually stating that if X does teach himself, the world must be flat, whereas in line 2, we're only saying that that fact, that statement of line 4 is the same as the statement of line 3. Okay, so in line 2, we're not stating that X does not teach himself or X teaches himself. We're just saying that these two are equivalent. Okay, the proof is not finished yet. We see that Sophia didn't give us any proof yet. There are a few more lines, and the idea is for us to figure out these few more lines together. And the way we figure this out together is a very general method in mathematics. You see what we could do, and whatever simplest idea comes to your mind, you try that, and often it works. So here's the question. What do you think should be the next line? What shall we tell Sophia to carry out as the next step? What can we conclude from the information we have so far? So what do we have so far? We have this initial long assumption, which we already made use of to get the second line, which says that X teaching himself is the same as X not teaching himself. Then we have the third assumption that assumes that X does teach himself. And the fourth line, which says that if X does teach himself, then the world is flat. What do you think we will be able to conclude after this as the next step? So let me give you a hint. What can we conclude just making use of these two lines, nothing else? Can we make any conclusion from these two alone? Okay, so when something is challenging in mathematics, we want to draw pictures and analyze things to come up with an idea, right? So let's do that. So let's analyze those two lines. On the third line we have, and I'm going to now rewrite it in usual words in the language of our intuition. Let me remind you something. If we go back all the way here, we pointed out in section 2 that there are 3 layers of thinking. The first one is the intuitive layer. The second one is the formal layer, and the third one is the computational layer. So the computational layer in our case is the language with which we communicate with the computer. So that's this program here on the left side. That's the computational layer. That's the language of interacting with the program, with the computer. The formal layer is this, what we see on the output. This is mathematics being formalized in precise language. Now, there is also intuitive layer, which helps us with our intuition. So when we're stuck with something, we switch to the intuitive layer to help us. And that's what we're going to do now. Intuitive layer is using as much ordinary language as possible. And so we're going to rewrite lines 3 and 4 in ordinary language. Line 3 tells us that X, in ordinary language, it tells us X teaches himself. Line 4 tells us if X teaches himself, then the world is flat. So why does it tell us that? Remember, the column here is implication, and we're saying, given that X teaches X, it implies that the world is flat. So it's exactly to say that if X teaches himself, then the world is flat. Now, from these two statements, can we make any kind of conclusion at all? We have one answer, a negative one, saying, no, we can't make any conclusions. Let me translate this to something even more intuitive. I'm going to tell you two statements. Okay, very good. We got a very good answer now in chat saying that we can conclude the world is flat. And indeed so. There is also another answer saying that we can conclude basically intuitive version of the last answer we see on chat is saying that we can conclude from this, implies that. This is not correct because we didn't say if this is true, then that is true. The third line was not the third line is assumption. Okay, no, I take it back. Sorry. What Shane wrote is also correct. We can also make that conclusion. In other words, we could step out from the assumption block. We could do synopsis here and step out. So let me show you what I mean. So I'm sorry, Shane. Originally, I thought what you said isn't correct, but it's actually correct. It's not going to be useful though, but it's still a correct statement to make. So if I do a synopsis here, I would step out and I would get something very long here, which is exactly what Shane wrote there. But we will not. I mean, we will get stuck in the proof after that. We want to simplify things, not to make them more complicated. Sometimes we have to make things more complicated before we can simplify them, but not this time. So this will turn out not to help us too much. But what Zizipo told us is the thing exactly that will help us. That from the fact that X teaches himself and the fact that X teaches himself implies the world is flat, we can conclude the world is actually flat. And just to reiterate this on a different example, imagine I tell you, as you know, I'm giving this lecture from Stellenbosch. And so imagine I tell you that if it's a sunny day in Stellenbosch, then I'm happy, right? That's one statement. If it's sunny in Stellenbosch, I'm happy. And then I tell you another statement. I say, in Stellenbosch, it's a sunny day, right? And from these two statements, you can immediately conclude that I'm happy, yeah? So that's exactly the same logic here. In other words, this is exactly the same deduction rule of D. We're saying, if we have this, then we have that. And we do have this left-hand side in line 3. So we just apply the D rule. Except that previously when we apply the D rule, let's say on the second line, we had to give a value to a variable. But in the line 4, we don't have any variables anymore on the left side of column. We only have a statement. So Sophia will just have to confirm that the statement on the left side of the implication can be found in the rest of the proof. And it indeed can be found because it's on line 3. So we will be using the D rule here. And remember, the first parameter now needs to be the line inside which our implication resides, and that's line 4. And then the next parameter was supposed to be the coordinates of the value of my free variable, but I don't have a free variable on the left side. You see, capital X here is not a variable, as we discussed. It's not, it is a variable, but this capital X at the same time already appears there. And once capital X has been introduced in line 1 as a statement, it now, after line 1, it now obtains some specific, possibly imaginary, but some specific value. So we can't treat X as a variable anymore once it has been given to us. It's a bit like this. When you solve a mathematical problem with variables, right? You introduce variables because they can change, but during the solution of the problem, once you're already working with X and Y, you can't change them all the time anymore, right? So it's the same situation. We already, from line 1 onwards, we're already working with some specific X, even though it was general in line 1. And so we can't change its values anymore. So X is no longer a variable as far as this line is concerned. And moreover, the left side of the implication doesn't even have any separate variables, right? So we don't need to worry about the second and neither the third parameter, because remember, the third parameter here with the D rule was telling us the position of the implication, but here in line 4, there is only one statement, so the position is unique. So we don't have to enter the other parameters, and we can just run this. And as expected, and as suggested by Zezepo, we got the conclusion that the world is flat. And it is now that we're going to use Shane's idea. We're going to step out from the assumption block. So we assumed that X teaches himself, and from this we got a conclusion that the world is flat. And maybe we want to step out from this, because if we do step out from this, we're going to get the following. Which is identical to what we had in line 4. But the difference is that in line 4, we had this inside another assumption block, and now we took it out. Think of it like working out with a very complex mathematical computation when you want to take some inner part of your formula outside. Okay, that's what we did it in the logical world. And then again, so this is, I kind of told you now for free what the next line should have been, but now I'm going to ask you again to make a suggestion. What do you think should be the line after this? So now that we took this one out, we can't anymore rely on these 3 lines. This is assumption we abandoned, so we can forget about these 3 lines, and we can just think of this line and that line. And do you think we can make any conclusion from these 2 lines, line 2 and line 6? Would line 2 and line 6 allow us to make any conclusion? So let's translate it in intuitive language as well. So basically, line 6 tells us that X teaching himself implies the world is flat. And line 2 tells us that that fact is the same as the fact as that X teaches himself. So in line 2, this thing is equal to that thing, and that thing exactly appears as line 6. Can we make any reasonable conclusion from there? So when we work out a mathematical proof, we want to, okay, so we can't yet, I'm now responding to the post. We can't yet conclude that the world is flat. If we wanted to conclude the world is flat, we should have had this as a separate statement. And so far we don't. But maybe we can still get this as a separate statement, as a separate line in the proof, by making use of line 2 and line 6. So trying now to achieve what Oriomi is suggesting, would we be able to, in the next line, have Sophia conclude this, namely that X teaches himself, from this fact and the fact stated in line 2. And let me just give you a little hint. Remember, we have equality here, and equality allows us to substitute things. I mean, let's abstract it away from the concrete situation to see the bigger pattern here, the broader pattern. Imagine I had A equals B, right? That's my line 2, something equals something. And then on a separate line, I had B. And now I want to get A. Can I get A from A equals B and B? Remember that this equals for us is now logical equivalence. So we could also think of it this way, right? So we know that we are told that B is true in line 6. We are told B is true. In line 2, we are told that A is actually equivalent to B. Is it possible to conclude from this that A is true? And if yes, then how? Would anyone like to explain how? Which deduction rule would we have to use? We can't use the deduction rule because the deduction rule applies to implication, whereas here we have equality. So deduction rule is not possible. Clearly, assumption rule would not be possible. We don't want to assume anything. We want to conclude something. What are we left with? Well, synopsis doesn't make sense because we're not stepping out of any assumption block. There's only one rule that we know that we're left with, right? Which one is that? Exactly, right substitution. We now want to, we should just check whether it's right or left substitution. So we basically want to replace this whole thing with that. So it is actually right substitution. We're going to be, no, it's actually left substitution, I think. Because the equality in line 2, we want to use the left side of the equality as our new thing. So it's a rule that's symmetric to right substitution, which is called left substitution, and it works the same way. So now I've forgotten the syntax for it, so I'm going to look it up by asking for help. And I look here at left substitution, and it. So this first parameter tells me the line at which equality should be. Second parameter tells me where we are substituting the line of that, wherever we are substituting. And then this tells me the occurrences of variables in the order in which I'm going to substitute my values. Okay, so I've sorted with that. I can go back now to this thing here, and I have to give the line number of the equality that I'm using for substitution, and that's line 2. Then I have to give the line number of where I'm substituting. So I'm going to be substituting in line 6. And because there is only one position in line 2 and there is only one position in line 6, there are no other parameters I need to give. And also there is only unique appearance of the thing I'm substituting, namely this thing. And so I don't need to list those appearances as well. So I can just drop all the other parameters and just run this. And when I run this, I see that as an output, I get x teaches x. And now one final step remains to get from x teaches x to the world is flat. You see, the previous line tells us if x teaches x, then the world is flat. And now we have, in this next line, we have the world, x does teach himself. Huh? And so now we can apply the idea of Oryomi that was pointed out a bit earlier to use the deduction rule. So we do the deduction rule, and the implication, the line at which the implication resides is line 6. And I don't need to give any more information, because just like before, we have no variables to concretize and so on. And we finally get the world is flat. So with this assumption, with the first assumption, first line, that we have x, an ideal teacher. So the fact that x is an ideal teacher is stated here. Namely, we define ideal teacher to be someone who teaches only those who can't teach themselves. The existence of such x implies that the world is flat. That's all we wanted to prove. So we can step out of this assumption now. And once we step out from the final assumption block, we have the theorem. So unfortunately, an ideal teacher does not exist. Any questions? Well, either an ideal teacher doesn't exist or the world actually is flat. One interesting thing about this proof, of course, is that you could put anything you like in the place of world is flat. The proof would still work. So whatever thing you put here, you will always be able to, in the end, conclude that after assuming that such x exists. So it's not really a single theorem, it's infinitely many theorems at the same time, because you could have anything you like to put there. Okay, so if there are no questions, then at least I would like to invite for reactions. So what we did now with this proof, was it very confusing, a little bit confusing? Was it understandable? It would be nice to have some reactions, please. A little bit confusing. Confusing, okay. Okay, good. So you see, a little bit confusing. Understandable, but needs more study. I must say the following, that this proof, which, as we seem to agree, is at least a little bit confusing, at the same time involves several key deduction steps in mathematics. And these are this D step, when you apply implication, the assumption step, stepping out from assumption, the synopsis rule, and substitution, left and right substitution. And in a way, these rules actually is enough to do all of mathematics. So this proof is a nice proof in the sense that it exposes to us all the tools we need for everything in mathematics. Everything except some axioms we might want to propose. And so the complexity of what we did now is expected, because you don't expect mathematics to be trivial completely, right? But at the same time, it gives, I think it gives some hope, because if you can understand this proof very well, then you should be able to understand the rest of mathematics as well. Because really, any kind of proof in mathematics decomposes into these fundamental deduction rules that are illustrated in this proof. This is why I like this proof a lot. I also want to make a remark about the process of proving. I think it was, even though this Russell's paradox idea in general might be easy to comprehend, or maybe not, but the process of finding the proof, even when the intuition behind the proof is easy, might not be easy at all. We had to do two kinds of steps. One are highly non-obvious steps. Like, for example, when we made this assumption in line 3, it was highly non-obvious. Why would we do that? Why did we make specifically this assumption and not some other assumption, right? On the other hand, in line 4, when we made the right substitution, that was easy. That was just looking at what we have, what data we have, and recognizing, okay, we have this as an assumption, and so this equals that, so why not use substitution just because we can, right? So this step wasn't so complicated, perhaps. The next step was also not so difficult. Just knowing that we have this line 4 and line 3, we immediately see, okay, we could make this as a conclusion. But then deciding to step out from the assumption, right, is a very highly non-trivial step. So how do we know that if we step out from this assumption, we'll be okay? We don't know, you see? This is a highly non-trivial step. Line 7 was an easy step because we just use substitution again. So every time we use substitution, it's not so difficult to figure it out because you have few equalities and you just try all the substitutions and see what happens. So it's not so difficult to get to line 7. Line 8 was also not so difficult because we just use the deduction rule, application of the implication. Now, the last line we could say was not trivial because, again, how do we know that we are done? We can step out, but we know that we are done if we know what we're proving. So maybe the last line also wasn't so difficult. So you see, a mathematical proof, as you've surely experienced in the kind of mathematics you've done, consists of two types of steps. One is where we do something that's kind of suggested by computations, by some substitutions and so on. And the other are highly non-trivial steps where we either introduce an assumption or we decide to step out from an assumption block. And so if we want a computer to help us in a proof, the part that's kind of trivial, the computer will be able to do. But the non-trivial steps is the ones where the computer might take a long time to computationally, the time might be too long in order for a computer to meaningfully help. So proof assistants are not able to help us in the difficult parts of the proof, only for the easy parts. It might be easy for the computer, but it still might be difficult for us in the sense that it requires maybe 1,000 substitutions, right? So if it's just a matter of trying out 1,000 substitutions, this is something a computer can do very easily. But we need to think of a new assumption or decide to step out from the assumption. These kinds of steps which require an intuition of a mathematician are very challenging for the computer. And if the computer just tries all possibilities, the number of possibilities very quickly become too large. Okay, so there is a question on chat. Can I ask what was the reason we need to have big X and small x in the first assumption? Also, did we also assume that small x exists? This is a very good question. The reason why, so it has two parts and I'm going to answer each separately. The reason why we had big X and small x is that we actually, if you look at the first statement, right? If you look at the first assumption, it's the big X that has been declared to exist. Small x doesn't exist. If small x existed, it would have been declared separately. Small x is just a tool we use to express some property of big X. We want to say that X is an ideal teacher. And we express this by saying that whoever X teaches, that person cannot teach themselves. So this small x is simply that whoever, okay? So it's not really a specific person we identify in the beginning. We just use small x to express some property of big X. And that's, I think that answers both parts of the question then. So basically, if I go back here, did I have this somewhere? Let me check quickly. No, I didn't write this out. So basically, this part tells me that for every value of small x, something's going to happen. I'm not identifying one specific value of small x at this stage. I'm just saying that for every value of small x, something is going to happen. And that describes a property of big X, namely describes the fact that X is an ideal feature. Does that make sense? Okay, good, good. Thanks, Zippo. All right, so what comes next? Well, we reached almost the end of our lecture notes. There is still one more section called Axioms, and you would have to go through this section yourself to complete the last assignment for this week, which is due early next week. I was originally hoping to include this in the lectures as well, but there wasn't enough time. But I think it's actually not a very difficult section, the last one. And then next week, we're going to make sure that those who have been consistently attending at least, that everything we covered is understood. So the two lectures next week will be very much dedicated to answering questions you might have, and it will be actually also good to prepare questions if you want to, and looking various different examples of proofs to for us to digest these new ideas and for it to solidify in our knowledge. I would like to then conclude here. Ilya, you can take over.
Okay. What can I say? Thank you very much for the very interesting lecture. Yes, kind of hopefully people will be able to follow the last bit on axioms and yes, and start using the tool for the purpose which the tool was designed. Thank you very much. And I just wish to remind everyone that in the afternoon we're going to have a continuation on the Earth modeling and the climate change modeling lectures, and I need to thanks again, Zurab, and see most of you hopefully in the afternoon, and Zurab next week. Thank you very much.
Thank you. Bye.